Very good afternoon, dear students. So we are meeting today for part 2 of some basic concept in chemistry. Okay. Yesterday we have seen part 1 of the same chapter, and I do remember yesterday we have stopped at unit. Okay. And in that we have discussed MKS, CGS, and FPS type of unit. MKS means mass. Okay, meter, kilogram, second, centimeter, gram, second, foot, pound, second. Okay, but these units of system, these system units are outdated right now. And today what we follow is the SI system of unit. Okay, SI system of unit, which is abbreviation. Actual full form for the SI system is nothing but International System of the Unit. International System of the Unit. What happened in the 1960? The conference, General Conference of Measure and Weights have proposed this international system of unit. Okay, and this was appeared quite successful as compared to previous system. Why? Because this SI system is totally depend on the decimal point system. It was based on decimal point system, and that's why it's found to be a very fruitful as compared to previous one. Okay, now what happened? See here. So I again repeat, this is the successful system of unit having name SI system, International System of Unit, and that committee, that International System of Unit have provided some 7 fundamental quantities to us. Okay, 7 fundamental quantities to us with their unit and their representation. Okay, let us see one by one. Now see here everybody what happened. Physical quantity, physical quantity, their representation, their SI unit, Okay, so number 1 was length. Okay, number 1 was length. Then it was the mass. Number 3, it was the time. Okay, very fundamental quantity. Number 4, it was electric current. Let us write electric current. Okay, after that number 5, it was the thermodynamic temperature. Okay, after that we can write here amount of substance, which is very important in the chemistry. All are important in the chemistry. Amount of substance, or you can simply say matter. About matter we have discussed yesterday. And last one is the luminous intensity. Okay, so see carefully what I am saying. Length, it was L. Okay, mass, small m, time, small t, electric current, I. Okay, thermodynamic temperature, capital T, amount of substance, that is number of mole, we can write N, luminous intensity I, and here V. Okay, now what type of units are provided for this physical quantity? These are basic physical quantities by the SI. Let us see right now. Okay, so SI unit, length is nothing but meter. Okay, it was the meter, that is small m. Representation, mass, it was the kilogram. Okay, kilogram, small k, and here g. Time is nothing but second. Very simple to know. After that, electric current, that is what? Ampere. Here capital A. Then thermodynamic temperature. Okay, Kelvin. We use Kelvin, capital K, in the SI system, which is more updated right now. Amount of substance. Okay, so that is what? Number of mole, we can write mole concept, that is the number of mole. Luminous intensity, candela, it has a unit candela, representation C and D. Okay, so these are the basic or fundamental quantities provided by the SI unit or International System of the Unit. Now what happened? There are many more quantities like speed, velocity, density. So fortunately what happened? We can derive the unit of quantity like speed, velocity, density from these units. Okay, so So afterward, let us see one by one. Now what happened? Let us explain the quantities in sequence. In that, first we will see mass and weight. Okay, mass and weight. Mass and weight. Now what happened? Everybody see here. Both are appeared very similar. Both appeared very similar, but actually they are highly different. Okay. Now what happened? Mass. Everybody know. Whatever matter is available in the universe, every matter has a particular mass. Every matter has a particular mass or weight. Now we will talk about the mass. Now what happened? Mass is the quantity of the matter. What is mass? Mass is the quantity hidden in that matter. Okay. For example, this is the pack of chalks. Okay. So it has some quantity, it has some weight, it has some mass. Okay. So just like that, what happened? Mass. And mass doesn't change with the position of the substance. Okay. Mass do not change with the position of the substance. Okay. So that is called mass. While on the other hand, what happened? Weight. Weight is nothing but what? Weight is the combination of mass and its gravitational attraction towards the or from the earth. Okay, what is weight? Weight is simply mass as well as gravitational attraction, and therefore as far as position gets changed, as position of the matter gets changed, weight also changes. Weight do not remain constant as like mass, and therefore mass is more fundamental property. Listen to what I am saying. Mass is more fundamental property as compared to weight of the matter. Okay, mass of the matter is more fundamental as compared to weight of the matter. Why? Because it is unchanged with respect to position, while weight weight changes with respect to its position. Okay, now according to SI system, mass is expressed in terms of kilogram. Mass is expressed in terms of kilogram, while fractional unit of mass or fractional unit for mass is the gram. Okay. For example, in laboratory generally we take the chemicals in gram. We never prefer the weight of the chemical in terms of kilogram, especially in the laboratory. Okay. But kilogram is the SI unit of the mass. Okay. Kilogram is the SI unit of mass, and gram is the fractional unit of that. Okay. So this is about the mass. There is well-known relationship between kilogram and gram. Okay. We know 1 kilogram is equal to 1000, that is 1000 gram. Gram you can express in terms of simply G or GM. Okay. 1 kilogram is equal to 1000 gram, which is nothing but 10 to the power 3. As far as indices are concerned, 10 to the power 3 gram. Okay. So this is the relationship between the kilogram and simply gram. Okay. Let it be. Second property which you have to discuss here is the length. Now itself that name suggests us length. Generally, what happened in chemistry? We regularly uses the length, especially atomic radii, ionic radii. Okay, atomic radius, ionic radius. Bond length is there. Again, what we can say, bond length is there. Atomic radius, that is one of the type of length. Okay. Again, wavelength, especially wavelength of any kind of electromagnetic radiation. So what happened? Length generally measured in the meter. Okay. But whatever words I just say, that is the atomic radii, ionic radii, or simply we can say what bond length or wavelength of the electromagnetic radiation. It is very fractional. In that case, we measure them in terms of a nanometer or simply a picometer. So 1 nanometer is equal to 10 to the power minus 9 meter. 1 picometer is equal to 10 to the power minus 12 meter. Again, there is many more units. Micrometer, 10 to the power minus 6 meter. Millimeter, okay, 10 to the power minus 3 meter. Our very popular centimeter, that is called 10 to the power minus 2 meter. Again, decimeter, 10 to the power what? Minus 1 meter. You can see slowly the changes. Okay, so this is about the length. Now volume, number third. So observe this carefully, very useful data in front of you. Okay, now number third property, that is what volume. Now volume is not a fundamental quantity. Volume, V-O-L-U-M-E. Volume is not a fundamental quantity, but already I told you that we can derive the unit of non-fundamental quantity even right from the fundamental quantity. Now volume generally denoted by capital V. Okay, now we know volume is the space occupied by three-dimensional object. Okay, any three-dimensional object, even we occupy the space on the earth, it means we have particular volume. Okay, and remember one thing, volume do not depend on the shape, size. Volume do not depend on the shape or size. For example, we can write here the volume of liquid, volume of air, gas. Okay, generally measured in terms of liter. Generally measured in terms of liter. This relationship is very important. Listen carefully what I am saying. Okay, 1 liter is equal to 1 cubic decimeter. 1 liter is equal to 1 cubic decimeter. Okay, therefore what happened? 1 liter is equal to 1 dm into 1 dm into 1 dm. It is the cube of whole dm. Okay, cube of whole dm. So what happened? Convert it into meter, then 10 to the power minus 1 meter into 10 to the power minus 1 meter into 10 to the power minus 1 meter. Why? Because since 1 decimeter is equal to 10 to the power minus 1 meter. Actually, we are trying to derive the unit for volume here. Okay, what is our target? We want to derive the unit for volume. So it becomes what? 10 to the power minus 3 minus 1 minus 1 minus 1. Okay, addition of indices. M into m square into m cube. Okay, so 1 liter is equal to 10 to the power minus 3 cubic meter. This is also unit. Again, this relationship is very important. Okay, so this is the unit of volume. This is the unit of. This is the SI unit of volume. This is the SI unit of volume. So what we can say? We can say that SI unit of volume is the cubic meter or simply cubic centimeter. How? Again we can derive. Okay, this is the SI unit of the volume. Cubic centimeter is also a SI unit of volume. See how, let us write. Okay, so everybody just see here. We know 1 meter is equal to 10 to the power 2 centimeters. Isn't it? That is called 1 meter is equal to 100 centimeter. In that way, see here, 10 to the power minus 1 and meter means how many? 10 to the power 2. So it will be 10 to the power 2. Okay, here centimeter. Isn't it? Same and same. So here we can write cube. Okay. So what will happen? 10 to the power minus 1 into 10 to the power plus 2. It will become 10 to the power 1. It will become 10 to the power 1 whole cube. Here cm cube. So finally we can write what? 10 to the power 3 cm cube. Okay. So 1 liter is equal to how many? 1,000,000 cubic centimeter. So this is also a relationship useful for the volume. Okay. So what are the units for volume? Finally we can combine them. Hello, listen here. For volume, 1 liter is equal to 1 dm cube. Am I right? After that, 10 to the power minus 3 dm cube. Sorry, cubic meter. After that, 100 cubic centimeter. Okay, which is nothing but 100 milliliter. It means one relationship we got. What is that? 1 ml, which is equal to 1 cubic centimeter. So this is very important. This is very important. Okay. Next. What is next? Number 4. Okay. Number 4. That is density. Density is again not a fundamental quantity. Density is again not a fundamental quantity. But as I told you, we can derive their formula. Okay. Now everybody knows density is equal to mass upon volume. Am I right? Density is equal to mass upon volume. What is mass? Mass is nothing but your kilogram That's why kg divided by volume, it is the cubic meter. So this is the unit of what? Density. This is the SI unit of what? Density. Okay. Or in CGS system, if you want to write in the CGS system, kilogram means what? Gram. Meter means what? Centimeter. So this is about the, see here, kilogram per cubic meter is the SI unit of the density, and gram per cubic centimeter is the CGS unit of the density. Okay. So what is density? Density is simply mass upon volume. Now we discuss very important term. What is that? Temperature. Temperature. Everybody see here the spelling of temperature. Maximum time when we are in the learning phase, we don't know how to write the spell of temperature. Even I was making mistake by writing temperature. Pressure. Okay. So this is very simple task. Please remember, this is wrong. Okay. This is correct. Temperature. Now during temperature, now what happened? Especially thermodynamic temperature. Temperature, it measures what? Hotness or coldness of the matter, body. Hotness or coldness of the body or matter. Now there are three scales. How many scales are there? Three scales. First one is the degree. Okay, this is for degree. Celsius. Number one. Second one, which we have degree Fahrenheit. Degree Fahrenheit. So degree Celsius, degree Fahrenheit, and number three is the Kelvin. Okay, capital A. So these are the three scales where we can have the measurement of the temperature. Degree Celsius is generally calculated from 0 degree Celsius to 100 degree Celsius. 0 degree Celsius to 100 degree Celsius. Here we can calculate it from 32 degree Fahrenheit. 32 degree Fahrenheit to how many? Near about 212 degree Fahrenheit. Okay, and Kelvin scale. Now see everybody what happened. There is interrelationship between the temperature scales. These are the three popular scales. Even degree Celsius, degree Fahrenheit, and Kelvin. Okay, Kelvin scale, Fahrenheit scale, and Celsius scale. Okay, first we will see the relationship between Celsius and Fahrenheit. Now everybody see what happened. Okay, so see carefully what I am saying. So what is the relationship between degree Celsius and degree Fahrenheit? Okay, so all of you listen here. Fahrenheit is equal to 9 upon 5. Okay, inside bracket. So we can convert one into other into in that. Okay, plus 32. This is the relationship. This is the relationship. For example, if you want to convert 2 degree Celsius temperature into Fahrenheit, okay, put here 2 degree. Whatever answer you will get, that is the Fahrenheit. Whatever answer you will get, that is the Fahrenheit. We want to convert 2 degree Celsius into Fahrenheit scale. Then here there was degree Celsius. What is the value of degree? 2 degree. Therefore put here 2 degree. Okay, and calculate it. Whatever answer you will get, that is in the Fahrenheit. So in this way we can convert degree into Fahrenheit, Celsius into Fahrenheit, or vice versa. After that, relationship between degree Celsius and degree Kelvin. Okay, so all of you listen here carefully what I am saying. Kelvin is equal to 273.15 in plus degree Celsius. So this is the relationship, interconversion of Kelvin into degree or degree into Kelvin. So in this way we can have the idea of the temperature. Okay, so temperature is the basic fundamental quantity. Basic or fundamental quantity, and we have three type of scale: degree, Kelvin, and Fahrenheit. So in this way we have finished that quantity matter. Okay, so dear student, this is the end of our SI units. Now let us move towards the next topic of the chemistry, which is a very important. Okay, even it is a historical idea which we should know about that. Okay, now that is nothing but under the title some basic concept in chemistry, that is called what? Laws of chemical combination. See here, laws of chemical combination. Now everybody knows. You might have seen the reaction in the 10th standard that, for example, H2 plus half O2. Okay. So what happened? Here there is a formation of H2O. So here there is a combination. Do not think much about that. Simply combination, and after combination of the element, after combination of the molecule, we get particular product, we get particular compound. Okay. But what happened? Under the title laws of chemical combination, here elements are meeting together, gathered together, combined together to form a particular product, to form a particular matter. Now what happened? There are some chemical combination laws before the knowledge of molecular formula. Before the knowledge of molecular formula. So it was the history of late 17th century. Okay. Now let us see first law of chemical combination. That is nothing but conservation of mass. Everybody see here. Conservation of mass. Now what is meant by conservation of mass? I will explain it later. Before that, okay. So everybody see here what I am saying. Under the title laws of chemical combination. Okay. So before the idea, before the knowledge of molecular formula formation, we were working with the 5 chemical combination laws. Okay, 5 chemical combination laws. In that, first law was known as conservation of mass. Okay, and that conservation of mass was suggested by scientist. Okay, by scientist Antoine Lavoisier. Okay, Antoine Lavoisier. He was during 1743 to 17th century of 1940. Okay, he was French scientist. He was the French scientist. Now he did some experiment very carefully. Now conservation of mass. Okay, even for your kind of information, I would like to tell you that Antoine Lavoisier is also known as a father of modern chemistry. Again, in multiple choice questions, such type of logic can be asked, such type of questions can be asked. Who is the father of modern chemistry? Who is the father? Antoine Lavoisier. Okay, so how he constructed the conservation of mass? Okay, which is nothing but one of the law of chemical combination. Let us discuss that. So what happened? This Antoine Lavoisier performed a lot of reactions. For example, he had taken mercury. This is the symbol of mercury. Okay, and phosphorus. Okay, he reacted phosphorus and mercury in the presence of air, and he found that, of course, he has taken phosphorus and mercury in the presence of air. That was a combustion type of reaction. Combustion means what? Burning reaction. That was a combustion type of reaction, burning reaction. And as a result, he found that after the completion of reaction, the weight of phosphorus increases. Okay, so again for confirmation purpose, he did lot of reactions, and he found that the weight of increase in the weight of phosphorus, which was exactly the loss of weight of air. Whatever gain in the weight of phosphorus, that was exactly equal to loss of weight of the air. And by having this observation, he came to the conclusion that mass can neither be created nor be destroyed. How? According to his observation, according to the observation of Antoine Lavoisier, he found that mass of reactant. In reaction there are two parts. Okay. For example, H2 plus half O2 giving what? H2O. Okay. This is the reactant part, and this is your product part. And according to Antoine Lavoisier, he found that mass of reactant is exactly equal to mass of product. And he did this conclusion after a lot of reaction, after studying a mini reaction, mass of product. Okay, so this equation he came to the conclusion, and that conclusion is present in front of you. What is that? Mass of reactant is exactly equal to the mass of product. It means that mass can neither be created nor be destroyed. Okay, see here, whatever mass of phosphorus increases, that same mass was lost by the air. Okay, because air was the important component of that reaction. Okay, so mass can neither be created nor be destroyed. So this is called as conservation of mass. Conservation means what? It is conserved. It is conserved, neither be created nor be destroyed. Isn't it? Okay, so after conservation of mass, law of conservation of mass, actually it is the law of conservation of mass. Let us see a law of definite proportion. Okay, law of definite proportion. Everybody see what I am saying. Law of definite proportion. Law of definite proportion. Now, what is the meaning of law of definite proportion? It means that if we are taking the same sample from the different source, okay, there is a French scientist, Joseph Proust. Okay, French scientist Joseph Proust have taken the two type of sample of cupric carbonate. Okay, so one out of that two sample, actually both sample was of cupric carbonate. One was natural and another was artificial. Okay, now what is the content of the cupric carbonate? Everybody see here. Copper, then carbon and oxygen. Okay, now what are both natural cupric carbonate and artificial cupric carbonates contain the same composition by mass, composition by weight, or the copper, carbon and oxygen. And after verification, he come to the conclude that whatever may be the source, whether it is natural or artificial, whatever may be the source of a particular compound, the composition of the particular element remain same. That's why it is called a law of definite proportion. Sometimes it can also be called as law of definite composition. Okay, so this is about see here everybody what happened here in that case. It is about 51% point something. Oxygen is about 9 or 10%, and remaining 31 or 32% is by carbon. So this proportion remains same in case of natural and artificial cupric carbonate. So this was suggested by the French scientist. Okay, he was again by French scientist Joseph Proust, and that becomes the law of definite proportion or law of definite composition. Okay. So we will see next law of chemical composition. After law of definite proportion or definite composition, we will see the law of multiple combination or law of multiple proportion. So listen carefully what I am saying, everybody. Law of multiple proportion. Number third, law of multiple proportion. Okay, law of multiple proportion. Now what happened in this law? First we will see the father of this law, or who have suggested this law. So that scientist is very popular, John Dalton in the year of 1803. Okay, so it is found that one or two type of element, not type of element, or two or more element when combined together, two or more elements when combined together, they form more than one type of product. They form more than one type of product. And what happened according to John Dalton in the law of multiple proportion? So the statement is like this. Okay, in examination statement can be asked. Statement is like this: when element A and element B combine together, when element A and element B combine together and form more than one product. What I'm saying? More than one product. Then whatever masses of element B, whatever is the masses of element B that combine with the masses of element A, whatever masses of element B that combine with the masses of element A, always in the small ratio, always in the small ratio of whole number. Okay, always in the small ratio of whole number. Okay, for example, now this will be clarified after having proper example. Okay, for example, what happens when hydrogen, see here, when hydrogen combined with oxygen, see here what I am saying, hydrogen combined with oxygen, there is a formation of water. There is a formation of water. Again, one possibility is there. Already I told you, two elements can form more than one product. Okay. When hydrogen and oxygen combine together, there is a formation of water as well as hydrogen peroxide. Hydrogen peroxide. Okay. So what happens? Everybody see here. This is H2. Okay. Having molecular weight 2. Oxygen. Okay. So I am talking about this reaction. H2 plus half O2. Okay. So H2 means how many? 2 plus half O2 means molecular weight of oxygen is 32. Okay, molecular weight of oxygen is 32 divided by 2. So it will become how many? 16. So 2 plus 16. So here we will get 18. Okay. After that, everybody see here. In this reaction, what happened? Reaction is slightly different. H2 plus O2. So here what happened? 2 plus 32. So it become how many? 34. Okay. Now everybody see here. 2 plus 32. So it become how many? 34. So same masses. Sorry, different masses of oxygen. Say 16 gram and 32 gram. What I am saying? Different masses of oxygen. 16 gram and 32 gram combined with fixed mass of hydrogen, that is 2. Fixed mass of hydrogen, that is 2. So here what happened? It is in the ratio, form a ratio 16:32. 16:32, that is 1:2. Okay, that's why I would say when two element A and element B combine together and form more than one product, then whatever masses of element B, okay, that react with or combine with the masses of element A, always form a small ratio of whole number. See, this is the small ratio, 1:2. 16:32 means 1:2. So this is about the law of multiple proportion. Again, you can take many more examples. Similar example for when nitrogen combined with oxygen, there is a formation of nitrogen monoxide. When nitrogen combined with the oxygen gas, there is a formation of nitrogen dioxide. So here also you can get the exact application or confirmation of the law of multiple proportion suggested by John Dalton in the year of 1803. Okay, so this is about the law of multiple proportion.